Hey everyone, welcome back to my channel where we learn to be a better programmer. And in this video, I'm going to continue on my C++ machine learning tutorial, and we're going to implement a neural network. Before we get started, be sure to hit that subscribe button and turn on post notifications so you don't miss out on future videos. Okay, so it's been a long time since I revisited this tutorial, and there's quite a few things that have changed since I first started, since the last video that I put out. So where we last left off is, with the neural network parts 4A and 4B, we implemented this read CSV because we're going to use the iris setosa dataset instead of the MNIST dataset. While they're still compatible, that's all fine. We can use the MNIST if we wanted to, or we can use the iris, but iris will run a lot faster. So for the purposes of this tutorial, we're going to use iris, and then I'm going to use the same code to run an MNIST trainer, probably for a few hours, and see what the results are. Okay, and then I've also added a normalize function to the data handler. So this basically normalizes the values within a particular range based on the values that are seen in the actual feature vectors themselves of the data array. So pause the video if you need to take a look at this method and see what's actually going on here. But basically, I created a normalized feature vector instead of this feature vector that takes an integer data type. And then there's a normalized feature vector that's a double instead. So that's pretty much all I changed with respect to the data handling library. And then with respect to the actual neural network code, it's actually going to get a lot more simple. There's a lot of stuff that I was able to get rid of, and a lot of abstractions that I had that we actually don't need. So I'm going to jump right in, and we're going to start implementing this layer class, and we're going to see what that looks like going forward. Okay, so right now I'm just going to say public because I want all my members to be public. I don't really need to worry about access modification here. So I'm just going to say public, and then say int current layer size. So that's the size of this current layer, standard vector of neuron, a pointer to a neuron, and then we're going to say that's the neurons in the layer, and then we're going to have a standard vector of type double, and that's going to be layer outputs. Okay, and then we're going to have a constructor for a layer, and it's just going to take an int and an int, and that's going to represent the previous layer size and the current layer size respectively. Okay, all right, so that's all we need to do for layer. And then for neuron, it's pretty straightforward. So we're going to make everything public. So every neuron is going to have an output, and then every neuron is going to have a delta value that we need to update the weights. And then every neuron is going to have a vector of double weights. And then the constructor is going to take an int and an int, and then a method to initialize weights. Okay, that takes an int and an int. Awesome. Okay, and that's the template, not template, but the H file for the neuron class. Okay, so let's take a look at the network class. Okay, so this one's going to be a little bit more complicated. Again, we're going to make everything public, but basically it's going to be, we're going to have a standard vector of type layer, pointer to layer, we're going to call it layers, and then we're going to have a double learning rate and double test performance. So this is going to be what we use to output our test performance. And then we're going to have a constructor, so network of standard vector int the spec for our network architecture, so like the number of neurons in each layer, and then int, and then double, and we're going to talk about what those values actually are when we start the implementation. The destructor, which we don't really need, but just nice to have it, and then we're going to have the following methods to implement the training and all that other associated stuff. So we have a standard vector of double, we're going to say fprop, and then we're going to pass in a data point. Okay, and so fprop is actually going to return the vector of doubles of the last layer outputs. So that's going to really help us when we want to calculate the output error and so on. Okay, so then double activate, and this is going to take in a standard vector of double, and then a standard vector of double. Okay, so this is going to represent, we pass in the weight vector of a neuron and the input vector of the previous layer or the input itself. So this is basically the dot product of those two. Okay, and then double transfer or transfer is when we put it through an activation function. So that's that would be our sigmoid. So we take that output value from this activate step, and then we calculate the transfer. All right, and then double the transfer derivative. Double. All right, so this is just taking the derivative of the transfer function. So this is used for backpropagation, and we'll see that in a second. All right, so then we want to implement our backprop methods. So we're going to say void bprop. I'm going to take in a data point star data, and then I'm going to have up void update weights, and that's going to take in a data star as well. And I'm going to say int predict, and we're going to take in a data point. So this predict method is going to be really helpful for the validation and test phases because we actually this is going to return the index of the maximum value in the output array. All right, and we'll see what that looks like too. All right, and then we have three methods for train, and it's going to take in an int. The number of iterations is the int, and we have a double test, which returns the test output, and then a void validate, because we don't really need to return anything. Okay, so now we're going to go ahead and go into our source directory and start implementing these classes. So I'm just going to say new file in neuron.cc, and I'm just going to copy over these methods like this. And now I just need to say include neuron.hpp, and then pound include random, because we need to generate some random numbers. Okay, so neuron : sorry if I'm not writing clearly enough in C++. I've been writing a lot of Java recently. So generate random number of double min, double max. So this will enable us to generate a random number between a min and max value. So we're going to say double random is equal to double rand max. Okay, and then we're going to say return min plus random multiplied by max minus min. All right, let's name these parameters. So this is the previous layer size. All right, and then this one is the current layer size. So yeah, all right, so I don't think we actually end up using the current layer size, but we'll see what that looks like in a second. So initialize weights, and then we're going to pass in the previous layer size and the current layer size. All right, so let's implement this method here like this, and then we're just going to say previous layer size and then current layer size. And I was right, we actually don't need this, so I'm going to get rid of this, and don't need to pass it in the method, and then we'll update the neuron initialize weights as well. Okay. All right. So now initialize weights. Okay. So we need to initialize our random number generator. So what this looks like is default random engine. Oops. generator, and then we're going to say standard normal distribution of type double, and then distribution, and so this is our mean, and then this is our standard deviation, I believe. Yep. Okay. And so then we need to initialize a weight for every output of the previous layer. So what that's going to look like is, say, for int I is equal to 0, I is less than previous layer size, I plus plus. And we're going to say weights dot pushback of generate random number between negative 1.0 and 1.0. Nice. All right, so that's all we needed to do for Neuron. So let's create a new file called layer.cc, and we're just going to say pound include layer.hpp, and then all this is just we need to implement the constructor. All right, int previous layer size and int current layer size. Okay, and basically we need to create a neuron for each for the current layer size. So the number up to the number of up to the current layer size. So we're going to say for int I is equal to 0. Oops, I is less than current layer size, I plus plus, and we're just going to say neurons dot pushback of new neuron of previous layer size, and that's it, because we don't actually need this current layer size value. Right. And I still need to actually pass in the current layer size. Okay, awesome. And then this layer outputs dot pushback of 0.0. All right, we actually don't end up using this layer output, so I'm going to get rid of this statement here. And this current layer size is equal to current layer size. All right, awesome. So that's all we needed to do for the layer class. And then we need to actually do the meat of our work, which is network.cc. Yeah, we don't need thread. Okay, so network. So let's implement the constructor. We're going to say network. Oops, network standard vector type int, and this is going to be the spec, and then int input size, int num classes, and then double learning rate. All right. So what this looks like is we're going to say for int I is equal to 0, I is less than spec dot size, I plus plus, and we're going to say if I is equal to 0. So this is when the input vector is our actual input to this layer. We're just going to say layers dot pushback new layer of input size, and then this current layer size has to be spec dot at I. Okay. Whoops. That's some weird syntax there. Okay, so that's basically saying the layer size that we this current layer size that we're going to create needs to be whatever it is at the spec, but the input is actually the size of the feature vector that we're actually going to have. Okay. Otherwise, whoops, I don't want to do that. Otherwise, it's just going to say layers.pushback of new layer of layers.at I minus 1, because that's the input of the current layer is the previous layer's size, neurons.size, and then spec.at I. All right, awesome. So that's all of our hidden layers. And then lastly, we need to add an output layer. So pushback new layer of layers.at layers.size minus 1 of neurons.size. Okay, so that basically just takes the last layer and gets the number of neurons that takes the last hidden layer and gets the number of neurons. That's all that's doing. And then the output size, the current layer size, is equal to the number of classes. All right, so then we're going to say this dot learning rate is equal to learning rate. Nice. All right, so that's our constructor. All right, so then we're going to say network of our destructor, and then we don't need to do anything. And then we're going to say double network activate standard vector double weights and standard vector double input. All right, so so what that looks like is we just basically need to have an accumulation value and create the dot product here. All right, so what this looks like is I'm going to say double activation is equal to weights dot at weights dot back. Okay, so the bias of a particular neuron is actually the last value in the weight vector. And let's just verify that we did that. So it's actually, this actually needs to be +1. So yeah, so we're basically saying that we're going to add an additional bias term to our weights just by adding a value from the previous layer size to the current layer size. Or yeah. Okay, so back to network. So this is the bias term. All right, and then we actually are just going to do the dot product. So we're going to say for int I is equal to 0, I is less than weights dot size -1, I plus plus, because we want to ignore that bias term. Then we're going to say activation plus equals weights of I multiplied by inputs of I. And then we just want to return activation. All right, awesome. So that's activate. And then we need to do the transfer function, which in this case, we're just going to use the sigmoid. So we're going to say double network transfer. And that's just going to take in a double activation value. And all this is going to do is going to say return 1.0 divided by 1, the quantity 1.0 plus exp of negative the activation. Like that. All right. So that's all that we need to do there. And then we're going to do network dot transfer derivative of double output. And all this is going to be is just going to be the derivative of the sigmoid, which I'll link to the documentation or the definition of the sigmoid derivative on Wikipedia or something like that in the description. So output multiplied by 1 minus output. Okay. And okay, so now we're going to get into the meat of our code, where we're talking about. So this is actually input, and we're going to implement the Fproc method. So actually, yes. So standard vector double, and this is going to be network Fproc. That's going to take in a data point like this, and I'm going to say standard vector of double inputs is equal to dereference data, and then we're going to say get normalized feature vector like that. And we're going to say for int I is equal to 0, I is less than layers dot size I plus plus, and we're going to say layer pointer to a layer is equal to layers dot add I, and we're going to say standard vector new double new inputs. So this is going to represent the inputs that we're going to overwrite. Okay, and we'll see what that looks like in a second. So we're going to say for neuron n in layer of neurons. So for each neuron in that layer, we're going to get the activation. Double activation is equal to this activate of in weights inputs. Okay, so we're just doing that dot product, and then we're going to say n dot output is equal to this dot transfer, oops, of activation. All right, so that's how we activate this particular neuron, and then we're going to say new inputs dot pushback in output. Okay, so what this means is basically that the new inputs are going to represent the output layer's outputs, or this current layer's outputs that we're going to actually overwrite this input value with. Okay, so what that looks like is we're just going to say inputs is equal to new inputs, like this. All right. And then lastly, we just want to say return inputs. Cool. All right. So on the last iteration of this for loop, that means that new inputs is actually the output vector of the output layer. So that's why we want to get this back. So that's treat that. Think of this last, what we're returning as the output layer outputs, which is our prediction. Okay. All right. So now let's go on and do Bprop. So full disclosure, it took me a really long time to get this Bprop algorithm to work properly. So don't get discouraged if you have to, really think hard on how this all comes together. If you have any questions, please leave comments in the description or comments in the comment section below, because it is kind of hard to visualize unwrapping the chain rule over and over in a reverse fashion like that. So anyway, so what we need to do is we basically need to backprop from the output layer all the way back to the input layer while calculating the error contribution of the previous layer to the current layer's output error, if that makes sense. I know it's pretty complicated it's not too complicated if you think about it in terms of like one layer and one neuron, but when you start to talk about contributions from multiple neurons from the previous layer, it gets kind of weird to think about. Okay, so I'm just going to write this code and we're going to see what it looks like. So int I is equal to layers.size minus 1 because we want to go from output to input. So while I is greater or equal to 0, I minus minus. All right, and so we're going to say layer, pointer to a layer is equal to layers.add_i, and standard vector double errors. So this is how we're going to accumulate the errors of a particular layer. So if I is not equal to layers.size minus 1, then we want to say for int j is equal to 0, j is less than layer neurons.size j plus plus. Okay, so we're iterating over every neuron in the current layer, and then we're going to say a double error for this layer, a double error for this neuron is going to start off by being 0, and we're going to say for neuron. No, I'm sorry. This is going to be, yes, I'm sorry. This is actually the error for this particular neuron in this layer, but based on the contribution from the based on this is the error that contributed to the error of the next layer, if that makes sense. So we'll see what this looks like. So layers.at I plus 1 dot neurons. Okay, so this is getting the neurons of the next layer. Okay, so if there's a layer right before the output layer, that's what if we're at the layer that's right before the output layer, then this statement is getting the neurons from the output layer. Okay, so now we're going to say error plus equals n so the next layer's neuron, the next layer's neuron dot weights, so that weight at J. So this current, so the current jth neuron in this current layer, its contribution here, so the weight at the next layer's neuron is J, multiplied by n times delta. Okay, I know there's a lot going on there, but we'll see what this looks like in a second. Okay, so this is accumulating this current neuron's contribution to the error of all of the nodes in the next layer. All right, so and then we're going to errors dot pushback error. All right, so that is what we needed to do for all other layers except for the output layer. So the output layer is actually a lot easier. So we're just going to say for int j is equal to 0, j is less than layer neurons dot size j plus plus, and all this is neuron star n is equal to layer dot neuron, oops, neurons dot at j. All this is errors dot pushback of double of data get class vector dot at j minus n dot output. So the output error is just the difference between the expected and the actual. Okay, expected minus actual. All right, and okay, so outside of this if-else statement, now we need to calculate the deltas for each neuron in the current layer. So for int j is equal to 0, j is less than layer neurons dot size j plus plus. Oops. All right, and then neuron star n is equal to layer neurons dot at j, and n delta is equal to errors dot at j multiplied by this dot transfer derivative of n dot output. All right, so this is the gradient slash derivative part of Backprop. Okay, awesome. So that's all we need to do for Backprop. So let's just run through this. So if the layer size minus 1, if I is not equal to the layer size minus 1, then we try to calculate the contribution of a particular neuron's error to the next layer's error. Okay, so the error signal of this current neuron is equal to its the sum of its contributions to the error of the next layer. Okay, and then for the output layer, it's very simple. We just take the class vector or the expected output and then subtract the actual. All right, and then we calculate the deltas using the errors at the specific neuron multiplied by the transfer derivative of that neuron's output. All right, and then next part is we need to write our update weights method. Okay, and then that's going to take in a data point as well, and what that's going to look like is standard vector double inputs is equal to dereference data get normalized feature vector, and for int I is equal to 0, I is less than layers dot size I plus plus. All right, and if I is not equal to 0, then we want to say for neuron in layers dot at I minus 1, right? So what this means is if we're at layer 1, we get layer 0, we get the neurons in layer 0. And then what we're doing with this is we're just going to say inputs dot pushback in dot output. Okay, So output. So what this is doing is we're taking the inputs of the previous layer. So we're creating the inputs of this current layer that we're updating the weights for is the outputs of the previous layer. Okay, and then we're going to say for neuron star in layers.at_i neurons. Okay, so this is the neurons of the current layer. And then we're going to say for int j is equal to 0, j is less than inputs.size, j++. And then we're going to say in.weights.at_j plus equals this learning rate, so the learning rate of the whole network, times n.delta. So this is the error for this particular neuron multiplied by its transfer derivative multiplied by the input from the previous layer. Okay, so that is how we update the weights for a particular neuron. All right, and then to update the bias, we're just going to say in.weights.back is equal to plus equals this learning rate multiplied by delta, like that. And we need to clear inputs, and then we're done. Okay, so that's the basic steps in our algorithm. So we're going to do Fprop followed by backprop followed by update weights. Okay, and then we need to implement this helper method predict. We're going to say data star data, and then standard vector output double outputs is equal to Fprop of data, and then we're going to return. We want to return the index of the max value of the outputs. So what this looks like, I'm just going to say return standard distance of outputs dot begin, and then standard max element of outputs dot begin outputs dot end, like this. All right. Okay. So now we need to implement our train, test, and validate method. So let's just make sure we have the signature right. So it's going to be void network train, and it's going to be int num epochs. Okay. And we're going to say for int I is equal to 0, I is less than num epochs, I plus plus. And we're gonna calculate the mean squared error here. So we're just gonna calculate the squared error, sorry, not mean squared. So it's gonna be sum error is equal to 0.0, and we're gonna say for data star data in this dot training data. Okay. So for every data point in the training data, we're just gonna say standard vector double outputs is equal to Fprop of data. And standard vector of int expected is equal to data.get class vector, and double temp error sum is equal to 0.0. Oops. And for int j is equal to 0, j is less than outputs.size, j plus plus. So this is how we're going to calculate the error for this particular iteration. I'm going to say temp error sum plus equals pal. So this is how we're going to square the difference in the values. So we're going to say double of expected dot at j minus outputs dot at j, and then we square it like this. Okay, and sum error plus equals temp error sum, and then bprop data, and then update weights data, and we just want to say after each epoch we just want to print the error. Okay. All right, and now we just need to do the test and validation method. So double network test, and we're going to say double non-correct is equal to 0.0, double count is equal to 0.0, and then for data star data in this test data, this, and then we're just going to do so increment the count, and then we're going to get the index. So we're going to say int index equals predict of data, and if data of get class vector at index is equal to 1, then we say num correct plus plus. And then at the end, we just say test performance is equal to num correct divided by count. And then we return test performance. Like that. And then the validate method is almost identical to this. So we're just going to say validate, and this returns a void. And we just use the validation data like that. And instead of returning something, we're just going to say printf. Okay, and that's pretty much it. So now we just need to actually implement our main method. So main, and then I need to fix this constructor. So basically, it's expecting it's expecting a vector, and two ints, or a size type, and an int and a double. Alright, so I'm just going to work on this makefile next, and then we'll be able to try this out. Alright, so this makefile is pretty similar to what we've done in the past. So we're just going to say source is colon equals to current working directory source, like this, and C flags. And then we just say standard is equal to C++11 -G dash, and that's it. Okay. And then our includer is equal to pwd include. Nice. And then all is just going to be main, and then our main target is going to be object. So our object target, and then source /network.cc, and obj that's layer.o, obj slash input, neuron.o. So that's all that is, and then it's cc, and then we use our C flags, and then source /network.cc -o main -l imnist ml root /lib this, and then -i, and we need to throw that. We just say -i, and then includer, and just to have a nice soft wrap like that, and we're going to say -i again of imnist ml root /include l data /obj /star.o. Okay, and so this object target is just if this directory is not present, then we just want to create it. This, then make dir obj. Nice. All right. And then obj slash layer.o is just dependent on source of layer.cc, and basically take the same command line like that. It's going to be a little bit different, but so our output is just going to be obj slash layer.o, and we only need our two include directories like this. Okay. And then we just want to throw a -c just to compile. So that's going to be the same for Neuron. So we're just going to say p this and Neuron. And this is Neuron. And Neuron. And then this is layer. This. And then we have a clean method. And all that's doing is rm-r main obj. Okay, so now let's test this out. All right, so let's just do make. Okay, so we got an error. Spelling error. Network.hpp vector. So I say make clean, make. Okay. So I'm getting an undefined symbol error because layer int is not defined. Perils of copying and pasting. Miss a few things. Okay, so let's run this. And here we have it. So it went through a bunch of iterations. So we have iteration 0 through 15. And we see that our error continues to decrease. And then our validation performance is about 85% prediction rate. But then our test performance is 100%. Okay, so that is pretty much all we needed to do to implement a neural network. Basically, this is a simple perceptron with backpropagation. But before I leave, I'm just going to make one small modification and use MNIST. All right, so now I'm going to hit main, and I'm just going to let this run, and I'm going to skip ahead to the end when we see some output. So I've let it run for a little bit. Some caveats here. I changed a few things, so instead of using the whole data set, I trimmed it down tremendously to let things run a little bit faster. So this means that there's 6,000 training data, 4,500 test data, and 300 validation. And as you can see, starting off on iteration 0, our squared error is rather high, right? And then by iteration 14, we see it start to drop quite a bit. So in our validation performance, we see that we have about 87% prediction rate, and then test performance is about the same. All right, so I really hope you enjoyed the video, and if you did, hit that like button and don't forget to subscribe so you don't miss out on future parts of this tutorial. All right, thanks so much. Bye.